Example 1.3.5, determine the doubling time for a growth rate of 1% per year and a growth rate of 2.5% per year. And it was stated in the text that this is going to be for a continuous growth rate, excuse me. So we were given the two growth rates of alpha equals 1% and alpha equals 2.5%. Normally we write growth rates as decimals, so 1 divided by 100 is 0.01 and 2.5 divided by 100 is 0.025. So those are the two givens that we were provided, and we are being asked to find, well, what was the doubling time? That's the symbol T sub D. Remember, doubling time is just how long does it take a quantity to increase by twice its initial amount. So to go from 100 units to 200 units, for example. So I'm going to derive the solution here because I think it's important that we understand where the concept of doubling time comes from. And if we're looking at a continuous growth model, which assumes that a quantity is continuously growing at all times, the model is the total amount at time t is equal to the initial amount times e to the alpha t, where alpha is the growth rate given in the problem statement and t is the number of years that we've let the time units that we have incremented related to the growth rate. So a doubling implies that our qt is twice q0, and so that's what we're going to use to derive the formula for TD, the doubling time. So we would just say that our final amount is 2q0, and it's q0 e to the alpha t. So that gives us our doubling amount, and so we can just solve this here real easily. We divide both sides by q0. That leaves us t equals e to the alpha t. Now we need to get rid of the exponential term. To do that, we use the natural logarithm, since we have a Euler's number, Euler's number, however you like to pronounce that, the e, the natural number. So ln of 2 on the left hand side, and ln of the right hand side just results in alpha t, but I'll write it all out here. So we got ln of 2 and then equals alpha t just by doing our exponential math. Okay, so if we want to solve for t, which will be our doubling time here, it's just ln of 2 divided by alpha, and that's the formula that was given to you in the textbook for doubling time of a continuous growth model. And so now you know where that came from, and where why the natural log pops up in that one. It's because we needed to get rid of that exponent term. So now what we need to do is just plug our growth rates into that to determine the doubling times. So fairly straightforward. It's just going to be ln of 2 divided by 0.01, and just pop that in your handy dandy calculator. You're going to get 69.3, and since our growth rates were in per year, that's 69.3 years. We can just repeat that for a growth rate of 2.5%, and we let's see, what is the calculation there? We get 27.7 years, and the units there come from whatever the growth rate was initially given in. So that's an example of continuous growth. We can see that the larger the growth rate, the faster that the quantity doubles. Also, continuous is the fastest growing of the three models. The exponential is a little bit less, and then the linear is quite a bit less than that. I think that summarizes it. The last point I wanted to make was that there can be some confusion between doubling times or growth models that are exponential versus continuous. And just remember, in this class, by exponential, what we mean is that the quantity increases in discrete units, like it compounds yearly. So you could think about, imagine that they put interest into your savings account only at the end of the year. So that would be a exponential growth model, like 100% every year. And then the continuous growth model is that you're constantly compounding, you're constantly growing. So those are often used for population estimates, because things are continually being produced. So we call that continuous growth. You might think of continuous compounding.